An object of mass 1 kilogram is attached to a platform of mass 4 kilograms with a spring constant of 400 newtons per meter. There is no friction between the object and the platform, and the coefficient of static friction between the platform and the ground is equal to 0.1. The object is placed at its equilibrium position, and then given a horizontal velocity v. So we need to figure out for what v will the platform never slip on the ground. So basically we're trying to figure out the maximum velocity that we can give this block so that the platform won't slip. So the force for an object on a spring is equal to the spring constant times the displacement it undergoes. So that'll be useful as we have Newton's third law, which says that each force has an equal and opposite reaction. So if we have the block stretching the spring, it's going to be experiencing a force pulling it back. So the force acting on the platform will be opposite that, but with the same magnitude. So this is one equation that we're going to need. And it will also probably be useful to figure out the maximum static friction. That is given by the coefficient of static friction times the normal force. And the normal force is simply equal to the sum of the two masses, so the total mass, times the gravitational acceleration. So we can figure out what the maximum static friction is, which is simply the coefficient of static friction times this quantity, or the normal force, which is the total mass times the gravitational acceleration. So now we have that. We should find the maximum force that this is going to undergo. So the maximum force, the Fmax, is going to be equal to the spring constant times the amplitude of the spring, or how far it's pulled. And this is simply an extension of this here, where the displacement is instead the maximum displacement, or simply the amplitude. So the maximum force is going to be equal to max force is equal to the spring constant times the amplitude. So now we should probably figure out what the amplitude is as a function of the velocity. So we can do that using energy conservation. So the total mechanical energy is going to be equal to 1/2 times the spring constant k times the amplitude squared. And this is because the potential energy of a spring is given by 1/2 times the spring constant times the displacement squared. In our case, the maximum displacement it will undergo is equal to the amplitude. So the maximum potential energy is going to be equal to 1/2 Ka squared. And this is also equal to the total energy, because at that point, all of the energy is potential energy. There is no kinetic energy. And this is also going to be equal to the maximum kinetic energy that the block will have. So when it has the maximum kinetic energy, it's going to have no potential energy at all. So these two are equal, and they are equal to the total mechanical energy of the spring, as the energy is transferred between the kinetic and potential types. So let's solve for the amplitude to get that as a function of the velocity v. So we can get rid of both of 1/2, and we just solve for the amplitude. A squared is equal to mv squared over k. So the amplitude is given by v times the square root of m over k. So that's our amplitude here. So now we can plug this value here into the equation that we found for the maximum force. So let's go ahead and do that right now. So the maximum force is given by the spring constant times this quantity here, which is the velocity times the square root of m over k. And we can bring the k into the square root to simplify it into the velocity times the square root of mk. This will simplify it a little. And so that is going to be the maximum force that it is going to experience. So now, if we want the platform to not slip, then this has to be less than the maximum static friction. So the maximum force exerted by the spring must be less than or equal to the maximum static friction that that's present between the platform and the ground. So if this condition is met, then the platform will not slip. So we just figured out what the maximum force was. And we also know what the maximum force of static friction is. So all we need to do is plug in this to our equation, which is less than or equal to this quantity, the maximum static friction. And we just need to solve for the maximum velocity, because we're trying to figure out what maximum horizontal velocity v that we can give the block without the platform slipping. So the maximum velocity must be less than or equal to the maximum force of static friction, which is the coefficient of static friction times the normal force, or the total mass times the gravitational acceleration, over the square root of little m and k. So now all that's left is to plug our values into a calculator to solve for v. So v, the maximum velocity v, must be less than or equal to the coefficient of static friction, which is 0.1, times the sum of the two masses, or the total masses, which is 1 plus 4, times the gravitational acceleration of 9.8 meters per second squared. Can divide that all by the square root of the little mass, which is simply 1 kilogram, and the spring constant, which is 400 newtons per meter. So I'm going to erase that to make a little more room. And now we just simply put this into a calculator to get that. That is about equal to 0.25, or a quarter of, or 1/4. So the maximum velocity is going to be, has to be less than or equal to 0.25 meters per second. So of course the maximum value will simply be 0.25 meters per second. And that is how you would solve this problem here.